Good morning, and thanks to the organizer for selecting our abstract. These are my disclosures. As you all know, today ibrutinib is the only BTK inhibitor approved for CLL treatment, while there are other second-generation BTK inhibitors with greater selectivity for this kinase that are being evaluated in clinical trials, such as acalabrutinib, which is already approved for mantle cell lymphoma, and spebrutinib, among others. Besides its obvious effect on the leukemic B cells, ibrutinib also affects other cells such as macrophages and neutrophils, which are key components of the innate immune system. Although infection rates during ibrutinib treatment are lower or similar in compared to other treatments according to published data, they are still a frequent adverse event, and they are among the most common toxicity leading to drug discontinuation, at least in the group of relapsed refractory patients. We think that to better understand the impact of these new agents on the immune cells may help to improve patients' care. Taking all this into account, our aim here was to investigate how second-generation BTK inhibitors, in particular acalabrutinib and spebrutinib, affects macrophage and neutrophil functions. First, we evaluate the effect of second-generation BTK inhibitors on macrophage polarization. It was reported previously that ibrutinib impairs macrophage polarization towards the M1 profile, which is a profile associated with a pro-inflammatory response and a more effective antimicrobial immune response. Here we evaluate how second-generation BTK inhibitor affect this. To this aim, we differentiate macrophages toward the M1 profile by using standard methods and from monocytes from CLL patients and healthy donor in the presence of ibrutinib, acalabrutinib, or spebrutinib, and then we evaluate the expression of these cell surface markers and the secretion of TNF-alpha and IL-10 that are markers that are differentially expressed on the M1 or the M2 profile. Here I am showing you how ibrutinib upregulates all the M2 markers and the secretion of IL-10, while it downregulates the secretion of TNF-alpha and the expression of CD86, which are classical M1 markers. And as you can see here, we found that spebrutinib did not modify any of the M2 markers, nor the M1 markers. Pointer is not working. While we found that acalabrutinib, similarly to ibrutinib, impairs M1 polarization. It is also known that ibrutinib affects macrophage response towards some particular microorganisms such as fungi, Mycobacterium tuberculosis, and also in response to the stimulation through key innate immune receptors such as TLR4, Dectin-1, and TLR2. Here we evaluate the effect of second-generation BTK inhibitors on macrophage phagocytosis by flow cytometry and confocal microscopy, and also the pro-inflammatory response by evaluating TNF-alpha secretion by ELISA. Here I am showing you the results of macrophage phagocytosis. As you can see here is phagocytosis of Simosan, Aspergillus fumigatus conidia, yeast of Candida albicans, and Mycobacterium tuberculosis, all inactivated. And as you can see, we found that macrophage phagocytosis was not affected by ibrutinib, spebrutinib, or acalabrutinib. Thank you. On the other hand, when we evaluate the secretion of TNF-alpha in response to this stimulation, we found that acalabrutinib, similar than ibrutinib, decreased the secretion of TNF-alpha in response to Aspergillus fumigatus, Mycobacterium tuberculosis, Candida albicans, and also in response to the stimulation of TLR2, TLR4, and Dectin-1. On the other hand, we found that spebrutinib only affected TNF-alpha secretion in response to Candida albicans yeast. Next, we move forward into evaluating the effect of second-generation BTK inhibitors on neutrophil response to fungal stimulation. We focus on fungal stimulation, given the importance of neutrophils in the immune response toward these kind of pathogens, and we evaluate the downregulation of CD62 ligand and the upregulation of CD11B, which are classical markers of neutrophil activation, and also the production of reactive oxygen species, all by flow cytometry. And here I'm showing you the results obtained with simosan. And as you can see here, in this case, we found that all the 3 BTK inhibitors, ibrutinib, acalabrutinib, and sperlutinib, significantly impair CD62 ligand downregulation, CD11B upregulation, and also RAS production. When we evaluate neutrophil-mediated phagocytosis of simosan, we found again that ibrutinib, acalabrutinib, and sperlutinib, they all impair neutrophil phagocytosis. I'm not showing you here, but same results were obtained when we used Candida albicans yeast. So we found that ibrutinib, acalabrutinib, and sperlutinib, they all impair neutrophil activation, RAS production, and phagocytosis of simosan and also Candida albicans yeast. And finally, we evaluate how second-generation BTK inhibitor affect the response of neutrophils towards Aspergillus fumigatus conidia that were heat inactivated. And in this case, we found, as it was recently reported by other group with ibrutinib, that acalabrutinib and sperlutinib did not impair CD62 ligand downregulation nor CD11B upregulation, but they all decrease RAS production and phagocytosis. So in this case, ibrutinib, acalabrutinib, and sperlutinib impair RAS production and phagocytosis in response to Aspergillus fumigatus conidia. So in summary, we found that both first and second generation BTK inhibitors have strong inhibitory effects on key innate immune cells. In particular, we found that in vitro macrophage polarization and activation in response to microbial stimulation were mostly affected by acalabrutinib and ibrutinib, but not by sperlutinib, while neutrophil activation was similarly affected by the 3 BTK inhibitors used here. So we speculate that this inhibition may impact on the antimicrobial immune response in vivo, and that should be taken into account, especially in the presence of other risk factors or heavily pretreated patients. Finally, I would like to thank to all the people that collaborate in this work, especially Ana Colado, who performed most of the experiments, also the International Workshop CLL and the CLL Global Research Foundation for the travel scholarship, and of course our funding agents. Thank you.